The Simpleton's method for numerical calculation of the sum of two squares, which states that an integer a squared plus integer b squared is equal to an integer of modularity 4n plus 1. My motto? Plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. 1. Every prime of modularity 4n plus 1 is a sum of two squares, such as 13 equals 3 squared plus 2 squared and 17 equals 4 squared plus 1 squared, whilst 4n plus 3 primes either singly or as 4n plus 3 times 4n plus 3 or 4n plus 1 times 4n plus 3 composites never ever result in sums of two squares, except as even powers, i.e. as squares. 2. If we multiply two 4n plus 1 primes together, then their product will also be a sum of two squares, but in two different ways. 3. We can only find out the sums of two squares for any 4n plus 1 prime by constructing it from the two squares directly and checking that the result is prime, or by repeatedly subtracting ever-decreasing squares that are less than the square root of the prime until the residual is itself a perfect square. 4. However, if we know the sums of two squares for any two primes, we can calculate the two sums of two squares for their product directly using the Fibonacci identity. 5. The Fibonacci identity is given by the algebraic equations a squared plus b squared times c squared plus d squared is equal to ac minus bd all squared plus ad plus bc all squared is equal to ac plus bd all squared plus ad minus bc all squared, and which show how the two sums of two squares results from the product of two 4n plus 1 primes, which are both the sum of two squares. Example 1 shows the calculation for primes 13 and 17, and the two resulting sum of two squares equations. Example 2 shows how multiplying the equations obtained by 1 by the sum of two squares of the third 4n plus 1 prime 5 results in a total of 4 sum of two squares solutions. 6. The Simpleton's method is simply numeric, no algebra, and for me is intuitive and therefore easier than the Fibonacci identity. Example 1, 65 equals 5 times 13 equals 2 squared plus 1 squared times 3 squared plus 2 squared. 1. Take the roots of the sums of squares for the two 4n plus 1 primes to be multiplied and insert into a 2 by 2 table with the roots of the largest prime in the top row. 2. Multiply the two roots of the large prime in the top row by the first root of the second prime in the bottom row and insert into the top row of a new 2 times 2 table. 6. Next repeat for the second root of the second prime and insert the results into a bottom row of the new 2 times 2 table. 4. Next we take the largest of the results and add and subtract the smallest one to give two new results, which become the top row of a new 2 by 2 table. We repeat what we have just done on the two remaining numbers, which become the bottom row of the 2 by 2 table. 6. Finally, for the four numbers we have ended up with, we take the largest and smallest, which become the roots in our first sum of two squares equation. And the two remaining numbers become the roots in the second sum of two squares equation. Job done. This slide shows the method confirmed for three pairs of 4n plus 1 primes. Whilst this slide shows two more examples. Example 4 shows the outcome for three 4n plus 1 primes using the results already obtained on the previous slide. Note that the sums of two square solutions obtained so far are all coprime in that the roots of the squares have no common factors. Example 5 is the same as 4, except we have multiplied by the square of the third prime. We again get 4 coprime solutions, but there are 2 more non-prime solutions which we get by multiplying the 2 input equations by 5 squared, so that the roots of the equations have a common factor of 5. It is instructive to repeat this calculation by first determining the equations for 5 times 13 equals 65 and 5 times 17 equals 85, and then for 6 times 85 equals 5525, when you will then end up with a total of 8 sums of two squares equations, the reason for which will become obvious. 7. A few miscellaneous facts regarding the sums of two squares. Euclid's Elements, Book 2, tells us 1. A squared plus b squared is equal to a plus b all squared minus 2ab. Proposition 4. 2. A squared plus b squared is equal to a minus b all squared plus 2ab. Proposition 7. 3. A squared plus b squared is equal to a plus b all squared plus a minus b all squared, all divided by 2. Propositions 9 and 10. 8. Every even power of a prime or a composite of primes of modularity for n plus 3 are factors of sums of two squares, i.e. 7 times 3 equals 21 has modularity for n plus 1 and is not a factor of any sum of two squares, but 21 squared is, so 5 times 21 times 21 is equal to 2205 is equal to 42 squared plus 21 squared, because 21 squared times 5 is equal to 21 squared times 2 squared plus 21 squared times 1 squared. Likewise, 3 squared times 5 equals 45 is equal to 3 squared times 2 squared plus 3 squared times 1 squared is equal to 6 squared plus 3 squared. So we can only conclude that 3 squared is equal to 3 squared plus 0 squared in order to preserve the sum of two squares criteria. My spiritual friend and soulmate, Mr. Leonhard Euler, although cognizant of this fact, was confused by it in Proposition 2 in a paper of his which can be downloaded from the Euler archive, Engstrom number 228. 9. In view of what we have deduced from the smallest primitive Pythagorean triple is not, as we are repeatedly told, 5 squared equals 4 squared plus 3 squared, but 1 squared equals 1 squared plus 0 squared, and which is always dismissed as being trivial. Since it is a founding principle of the integers, it is anything but trivial, but I will concede that 5 squared equals 4 squared plus 3 squared is far more interesting. If you have difficulty accepting the validity of 1 squared equals 1 squared plus 0 squared, and feel that it is an unjustified and trivial embellishment of 1 squared equals 1 squared, then consider the following. 1 squared plus 1 squared is equal to 1 squared plus 1 squared. Therefore, 1 squared equals 1 squared plus 1 squared minus 1 squared is equal to 1 squared plus 0 to the power half squared. Therefore, 1 squared equals 1 squared plus 0 squared. QED. Try it on your calculator. 10. Next, two odd or two even sums of two squares always give an even result. Hence, 2 is a factor, and therefore all are reducible to an odd sum of two squares by repeated division until the answer is odd. E.g., 90 equals 81 plus 9 is equal to 9 squared plus 3 squared, and 90 over 2 equals 45 is equal to 36 plus 9 equals 6 squared plus 3 squared. Two examples follow of repeated doubling for an odd sum of two squares. The footnote demonstrates the method of obtaining the sum of two squares for each doubling of the answer. 11. To conclude, this presentation has demonstrated that the sum of two squares integer number field, which is after all just the practical application of the Pythagoras theorem, is founded solely on the 4n plus 1 primes, the composites of those primes, the powers and doubling of both the aforementioned primes and composite, coupled with multiplication by the even powers, both prime and composite, of either modularity. It is therefore just speculative nonsense to conjecture that a 4n plus 1 prime could exist that was not a sum of two squares, and certainly does not warrant complicated abstract mathematical proofs that purport to establish the truth of the matter. What goes up must come down, and the Simpleton method is just as easily applied backwards as it is forwards, and so by infinite descent will always terminate with a 4n plus 1 prime, that is a sum of two squares, QED.